Hello, everyone. Thanks for staying to this talk. My name is Felipe, and today I'm going to be presenting some work with my advisor, Arnosti, about rapid rehousing. So specifically in this talk, I want to give a little bit of context of what rapid rehousing is. Now we have technology, it will go even better. Nice. So I'm going to give a little bit of context for everyone that is not familiar with what rapid rehousing is. And then I'm going to study two different types of prioritizations that we could use in this type of settings. So first of all, what is rapid rehousing? This is an assistance package that consists mainly of two things. So first of all, you get a caseworker. Oh, and this is an assistance package for household experiencing homelessness. That consists of two things. First of all, they will get a caseworker that will help them find housing. And secondly, they get some money to help them pay rent for a fixed amount of time. Right. Now, the main difference between this housing problem and other type of housing problems is that there's no fixed capacity. So the caseworker will go to the open market, to the rental market, and will look there for landlords that are willing to rent to these people. So therefore, that we don't have a fixed supply. This is really different from other type of resources that are used to help people in homelessness, like permanent supporting housing or transition housing. Now, this means that they have all of those difficulties. So now that we have a general idea of what rapid rehousing is and what it consists of, how is this done? Well, first of all, I need to give a little bit more context of what is the continuum of care. So the US is partitioned into different geographical regions called continuum of cares. How this partition is made, I don't think anyone knows, but the relevant part about this is that each of these geographical regions keep their own priority queue. That is, all the people that are experiencing homelessness, they will be put in the same queue depending on the region. And now, because how are these rapid rehousing being allocated then? Well, first of all, we have the caseworkers that work for nonprofits. They become available. So they get some money, they get some time to help some household, and they'll go to the CES and they'll tell them, who should I be helping now? The CES, in all of their wisdom, will have a priority queue, and they will say, this is the household that you'll need to help. The priority will say, okay, perfect, then I'll get to work, and then between the two of them, we'll find the housing in the rental property that the new house can move into. Now, from all of this talk is specifically about this. How does the coordinated entry system or this priority queue gets to choose their prioritization? Now, because they receive their own funding, this funding comes with certain guidelines that are kind of enforced. One of them, and probably the most important, is that the reason that we have a unique coordinated entry system is because we want to have a fair and efficient way of allocating resources, and in such a way that the more vulnerable people or the people with more service need are helped first. Now, that is great. We have a guideline. The problem is that we don't have any definition of what vulnerability is or service need is. And in fact, every CES has their own definitions. And even if we have a clear definition, it's not clear that helping the vulnerable or helping the people with service needs is the actual best thing we can do. So this work, what we'll try to do is analyze a dynamic model where our current decisions will affect the evolution of the system. Now, this has two nice things. First of all, is that this is a little bit more closely related with what happens in reality. People can become homeless repeatedly. And secondly, because we have a dynamic model and our decisions matter compared to a static model. In a static model, if we help one person, our benefit is exactly one, the person that we help in that moment. Now, in this dynamic model, we can actually make a little bit more operations problems and say, let's say we want to minimize the steady state homeless population. Then we can start analyzing this with some of our operating tools. So, yeah. So our question is, can we do this? And our main finding in this project is that there is some prioritization that actually does the trick. So now I'm going to spend some time building up to the entire model, because I think if you get the model, then we are like 90% through the talk and the results. So I'm going to start with one case with one agent, and this agent moved between two states. They're either housed or unhoused. And the time they stay in house follow an exponential distribution with weight lambda, right? And once they become unhoused, they might find housing without help. So this happens, people leave the CES just because they find housing independently. And the rate at which they find housing is mu(n). So in this case, we have our coordinate system, and this is pretty easy to calculate steady state. And now this is an important part of the talk. We specifically define vulnerability as the agent with a small mu. So you have two agents. The longer it takes you to find housing, the more vulnerable you are. Important definition here. Now consider the case where we have resources. So we have the same single agent, but now at a rate of sun r, resources arrive. And what this resource arrival makes is that you can move immediately once the resource arrives, an agent that was unhoused, you put them immediately into a house. So in this case, we have one agent, the decision is easy. Whenever a resource arrives, we just house the person that is unhoused. Note that because the arrival process is a boson, we still have a continuous temporal change, so it's analyzable. So now we can talk about the entire model. So we have a model made out of n agents. Think about the n agents, about all the people that live in the same continuum of care. So you might be housed or you might be unhoused. And think about the CES or the priority list as all the people that are unhoused at a given time. Right? We have our arrival rate of R. Whenever a resource arrives, we need to use it to move someone from the unhoused to the house state immediately. If we don't use the resource, we lose it. The question is, who should we be reaching? And the answer depends what's our goal. So first of all, we're going to define priority use. So if you remember, they have the guidelines to have a strict prioritization, or not a strict, but a prioritization of who should be helping. And the way we capture this is the definition of priority use. So the idea is you set for all of the agents in your system, you're going to choose a prioritization. Whenever a resource arrives, you see who's at the highest priority that is in-house, and you help them. So for example, two natural type of prioritization queues is prioritize the vulnerable. So a resource arrives, you see who is unhoused, look at the agent with the smallest mu, help them. The idea is that they will take a long time without help. And then the other natural idea is a resource arrives, you see who will make the best use of the resource, in the sense that once you help them, they will stay housed the longest. That will be likely to succeed. Now, our first result is that neither of these are good. The vulnerability is especially low compared to the likely to succeed one. And rather than focusing on the math says that you could do arbitrarily bad with any of these policies. I want to give you some intuition of why this is bad. So why can vulnerability be bad? Consider an example, we have 5 agents that are really, really slow at finding housing, but once they find housing, they're going to lose it almost immediately. And you have a big group, a really big group that is slow, not as slow at finding housing, but once you house them, they're the best, they're going to keep their housing a long time. So if we make a vulnerability-based priority, most of the resources are going to be wasted on the first group. Now, wasted is a strong word, but I would say could be better used in the second group in this case. Right? Second example, why can likely to succeed fail? Consider again 2 groups. We have the first group that is quick to find housing and rarely lose it. And we have a second group that is slow to find housing and also rarely lose it. So in this case, because the first group is keeps housing slightly more than the other group, we'll be giving resources to them all the time. The problem is that we give resources to them, they would have helped themselves if just waited a little bit. So we're kind of using the resources here in the first group, when using it in the second group will be way more efficient. So what do we do now? How can we solve this problem? Well, in order to do this, I'm going to make a little bit more math. So now I'm going to introduce a little bit more notation. So in general, a Markovian policy is a partition over the state space. So the state space is which agents are unhoused. And I'm going to say that PI are all the states where if a resource arrives and we are state on PI, agent I is going to get help. So they're going to move to that state. So I'm going to use xi I to be the variable that defines what the probability, well, it's drawn from the state distribution once you follow this policy, or what's 1 if the agent is unhoused and 0 if the agent is housed. And one last thing that I want to define is RI pi is given that you choose a policy pi, RI pi is the rate at which I'm helping agent I. So this is the rate at which agent I is receiving resources from the policymaker. And our first proposition is that you can actually calculate the steady state of a particular agent just based on the rate at which they receive resources. And it's this simple approach. And this simple equation gives us a couple of things. First, you can know that you can never give help more than lambda I, and the total rate at which I help people needs to be less than the resources that are. Those are the main things that you need to get from this equation. And in fact, our goal, if we could write a optimization problem, would be choose the partitions such that we minimize this and pi is the Markovian. The problem is that choosing partitions is hard. But imagine if we could relax this and instead of focusing on partitions, just drop partitions and just say, I want to give this number of resources to these agents at this rate. We can do that in practice, but if we put that would be great. We should pinpoint exactly who to help. And we would end up with a linear program. And this linear program, in fact, is a lower bound than the policy. And it also suggests a priority queue. And I would give you time to try to guess it. I think it's a good exercise, but because of time, I'm just going to say, choose the agent with the smallest lambda plus mu. So if you see this, the only variable in the objective is Ri. The smallest lambda I plus mu I is, the more I help you per resource that you. So our result says that if you choose this priority queue, choose the agent with the smallest lambda plus mu I whenever a resource arrives, this is pretty good. And by pretty good, I mean the difference between the unhoused population between this one and the lower bound that we found grows so linearly in the market size and the number of resources. So this is like a first nice result. Now, I want to say that in general, even the best Markovian policy might not be a priority queue. So that the fact that there is a priority queue that does well is a nice result in itself.
And you would tell us an intuition? What's happening?
Yes, so I will try to give 2 minutes for the intuition. So this policy that prioritizes base lambda plus mu is actually a greedy policy in the sense that you're maximizing the benefit of a resource. So consider 2 states. Consider a system with 1 agent in 1 state, and you duplicate this system. So you have the same system twice. On the first system, the agent receives a result. On the second system, they don't. So the benefit of helping them is the time until these systems recouple. And because everything here is exponential, that follows the expected value of the minimum of 2 exponential random variables. So in some sense, it's really in the maximizing the benefit of housing time of each agent. And now our main question of the talk is targeting the vulnerable good thing? And the answer is depends. If the vulnerable are actually the household with the smallest lambda plus mu I, then yes. But and then we would say that the vulnerable will benefit the most from resources. But the opposite could be true. So the vulnerable could be the agents that least benefit from resources, and then no. Right, is saying the vulnerable is not the same. It's not the optimal thing to do. Okay, so now I'm going to jump to a different type of prioritization. Okay, so we have the same in this new prioritization, we have the same agent dynamics, but now we're in the crazy world where we can't observe every agent's characteristic perfectly. So now we don't know the lambdas and mu. So because we're in this unruly world, when we can observe anything, we're going to give us some leeway and we're going to say the resource can be safer. I'm going to use F to define the waiting time policy. And the only thing I have right now is that on expectation, the rate at which I use resources in this waiting time policy is less than the actual rate at which resources are. And again, I have the same goal, set to minimize the unhoused population. So two fundamental, yes.
So what information do we know about lambda and mu? Nothing.
Nothing. The only thing you know about the agents is when did they join the queue.
So no distribution.
No. For people on OR, I think the first in, first out is bread and butter. And there's many ways that we can define this, but the main characteristic that I care about in this case is that the FIFO queue serves the agent that has been waiting the longest. That's how we're going to define a FIFO queue, and the LIFO queue is exactly the opposite. The agents that get served are the agents that have been waiting the least. And the result for this section is from any waiting time policy, another intervention, think about it, a waiting time policy. The 5Q is the best one at targeting the vulnerable. So you could choose whatever crazy way of like a lottery, different type of queues. And in any way you choose, a 5Q would be better at targeting the vulnerable. And the intuition behind this is that we define vulnerable as how long will it take you to find housing. So in some sense, the longer I make you wait to get a resource, the more likely you are to have a smaller meal. So it's nothing crazy. The crazy thing here is that I say it's better at targeting, and I don't define better at targeting, but I get to that. So we use the concept of majorization. So for anyone not familiar, if you don't want to focus on the math, just think about it this way. Order the agents from the most vulnerable to the less vulnerable, and then choose whatever cutoff. The 5Q will give most resources to the first group compared to any other policy that you choose. And whatever cutoff you choose, this will be true. That's the main idea of majorization. Then, as you would expect, because of the opposite definitions of LIFO and 5Qs, the LIFO is the one that targets the least, the worst one at targeting the vulnerable. And if we want to define this, we could say that if the vulnerable benefit the most from assistance, then the best thing you could do if you only have waiting time policies is use a 5Q. If the vulnerable benefit the least from assistance, then the best thing you could do is do a LIFO. And for a more graphical interpretation of this result, just think about it this way. So we have each dot is an agent. We have on the y-axis lambda and on the x-axis mu. And if we're in this whole scenario, then you want to help the agent with the smallest lambda plus mu, you're here. You want to use a 5Q or prioritize the vulnerable, both will lead to the same result. If you're in this world, then the agents with the smallest lambda plus mu have the biggest benefit, so you want to use a LIFO. Now, the unfortunate part is that you're in this in-between world where you don't have like an exact ordering of lambdas and mu's, then it's hard to tell what you want to do. So just a few key takeaways from this talk that I would like you to get over to go with is that focusing on either characteristic can be inefficient, but if you focus on both of them, you can do pretty good prioritization. And in terms of waiting times, I want to say that 5Qs are the waiting time that targets the vulnerable the most, and LIFO is the reverse. And from a more general or miscellaneous perspective, I want to say that clear definitions are important. You might disagree with our definition of vulnerability, but at least I know that we're disagreeing on the same idea. So I think that's important. Thanks so much. There's
I'm curious, your model is so general, it's continuous time markup chains and doesn't have to go on unhoused populations. I was wondering, are there other places you've seen where this kind of model comes up? So for example, I can have like a repair truck, and these are like in different facilities that break down at some rate and kind of have internal teams that could fix them at some rate. And then you sort of have the same problem. Like,
yeah.
are there places where these techniques come up that have nothing to do with housing?
That's a good question. I think that there's some literature on like those networks, like human networks that have some similar features like this. So you can think about like a factory where you have to go over the process. It's like those systems. But in more social good purpose application, we need to think a little bit more about